In digital signal processing, we often want to plot our signal. We want to visualize our audio waveform. And of course, this may seem easy, but actually to generate such a plot automatically and then save it to the disk is not so straightforward. So in this video, I want to show you step by step how I plot my audio signals and then save them to a file using Python. And if you're just interested in the source code, I have a link in the description to the gist on GitHub. So just feel free to check it out, copy, paste, use in our projects. But if you're interested and you really want to master how to plot such an audio signal with Python, then let's go with the tutorial video. So what we'll do is create a Python file, call it plot signal tutorial. As you can see, it's completely empty. So what we can do is create the standard Python boilerplate. Okay, so we have our main function, and what we can now do, we can generate the signal. But before we do it, we need some libraries. And well, how I like to do is I like to create virtual environments. So we are in this folder, and I can go Python -m vnv. Yes, I want to create it for this workspace folder. Exactly. Okay, perfect. And now I can see if I'm in this environment by calling which Python. As you can see, I am not in this environment, so I need to activate it. So the way to do it is vnv scripts and then activate. And I'm on using PowerShell, so I'll launch a PowerShell script. Okay, perfect. As you can see, I'm in here in my status bar, it says I'm in plot signal tutorial virtual environment. Okay, and now I can install the necessary libraries locally so I don't pollute the operating system globally. So what I'll need NumPy, I will need Matplotlib, and I will need pathlib. Perfect. As you can see, all the packages got installed, so we can go back to our script. Let me close this. And what we need to do, we need to import NumPy because we want to generate the signs. So we have our signal will be something like sine NumPy sine 2 times nppi times, and now the frequency times the time, and the frequency will set to let's say 440, and now the time will be dependent on the sample rate. So we need to define the sample rate, and I also like to say how many seconds our signal will be. So let's say 5 seconds. Okay, and now we'll have time is NumPy arrange length seconds times sample rate, and now we divide it by the sample rate. Okay, and now we generated our signal, and now we want to plot it. So we say plot signal. And now we need to plot our signal. So what you would typically do is you would go here, say signal, and then you would import Matplotlib pyplot as plt, and you would go plt figure, and I'd like to pass in the size 12.6, and you would call something like plt plot signal, and then we can call plt show. So now let's try running this. So how to call it like a Python plot signal tutorial. Okay, so there's a few things that went wrong here. So why you can see this rectangle instead of the signal? Well, because we plotted 5 seconds of 5 seconds worth of samples. So there's no way we could see all this. So let us, and there are also like a few other things that maybe not so nice about this plot. So what we can do is we can instead pass to our, let me just maybe minimize it a little bit, to our plotting function. I'll just pass in first 1,000 samples of the signal, and immediately you can see that we get a nice sign. But that's, you know, that's just the beginning of what we can do with it. Well, first of all, what I don't like is that the font here on this labels is very, very small. So we can easily fix this by running once per our program, plt rc params update, and now we pass in a dictionary font.size 20, and now we rerun again. Okay, and now we see that we got way better, way clearer labels. But I don't need so many ticks on the y-axis. So I can of course go to y-ticks 101. And as you can see, I got only 3 labels, and that's, in my case, that's completely sufficient. And now, let's say we want to plot this plot in some specific color. We of course can do it like this as well. So we can go color. I like to define it as a kind of a Python constant, and you know, WolfSound colors are EF7600, and it suffices that I pass here just this color as an argument. And let me run this again. Okay, and we got nice orange here. But what I still don't like is that in typical mathematical plots, we have an x-axis, right, and a y-axis. So we rarely have this kind of a box thing, and it doesn't look nice on plots. So what I like to do is, before we show this, I simply turn on this rectangle. Let me show you how. So we first get grip on the axis object, so we call plt.gca, and then we say x spine stop set visible false, and we can do the same thing here. We can go right, we can go bottom, and let us run this again. Okay, perfect. But now what we're missing is this axis here, right? We're missing the axis in the middle. It's typical. So what we should do is we should take the xlim value. So first we'll take how many of the samples we have. So we have samples count signal shape 0, and then we say xlim is equal to 0 samples count, and we'll now be able to plot here plt each lines, which stands for horizontal lines, and again we'll pass here 0 as the y coordinate, and then we pass in xlim of 0, xlim of 1, And we mark that we want to draw this axis with K. And what we also do, we also say plt xlim, xlim. And now we have the limit set, and we should get a nice axis in the middle. And that's exactly what we got. And also, as you can see, the plot starts at the 0 index. Okay, so that's way better. But what we are still missing are the labels, right? The labels. So what we can do here, we can set the Y label. So plt dot Y label, and this is of course amplitude, and we can call plt X label, and we go say samples. Okay, and I got this nice samples view right here, samples text here. What is also that I don't like as much about this plot is that it's a little bit too thin. It may not be visible everywhere. So what I like to do, I like to go here and say line width assign 3. Okay, and now that's way thicker, way more readable. But what if we want to have the time units instead of sample indices? Well, here we need to actually pass in then this time vector that we had. So to still allow to plot signals without the time vector, I can do it as an optional argument. So we can pass in time, but we can ignore this. And now here we can say, okay, if time is not none, then do some, maybe if time is none, okay, then we have our original flow, and also using this. But if time is not done, then we can go plt plot time signal color line width equals 3. And for this, we need to adjust the xlim now. So we'll have xlim is simply time of 0 and time -1, which is the last element in the array. And now let us execute this. Okay. I messed something up. Aha, yeah, okay, because I pass here just 1,000 elements, but more elements of times. Okay, let's do it again. Perfect. And now as you can see, I have a wrong label here. So let's fix this. Samples go here. And here we go, plt x label time in seconds. Okay, perfect. This is a very nice plot. We have amplitude over time. We have nice labels on the x-axis, nice label on the y-axis. This already looks pretty neat. The last thing that I'd like to show you is that, you know, typically you won't be interested in plotting something just to see it and then not saving it. And often if you run something on the server, right, you typically are not connected with your desktop. You cannot see the image. So it's typically worth knowing how to save such an image. So what we can go here and we can comment this out and we can say, okay, we want to save our figure. So go plt.savefig. And let's say we want to save it in some folder. So let me just go here and say, okay, something like image output path. I'll call path image. And for this, we of course need from Matplotlib import path. So we need a path to our image files. And I can go here and I'll go, okay, image output path. And let me call it something like signal.png. But actually, this is maybe not very flexible, but let me show you in a second why. Okay, and let us run this. And what you'll see that it will fail, right? Because there's no image directory. So we need to fix this by going image output path, make directory. And we say that make also all the parents. And if this exists already, then it's also fine. And we run this again. Perfect. We see that the image folder was created. I can go here and we can open this and we have a nice signal. What I also like to do is I like to set some parameters. And since these are often used between various plots, I often have them as constants. So I'll have something like save params. And here I have a dictionary. So the resolution should be at least 300 dpi. And then what I like to do also is have this bbox inches tight, because it allows us to remove the unnecessary white space around our figure. And then what I also like to do is to have the transparent background, so I can choose the background later on. So for this, you need to call transparent true. And now we can pass this to our saving function and say save params. Okay, and let's see how it looks now. Great, we got this nice gray background, transparent background, and we can set it to whatever we want. There's one caveat here that if we call show and then close the figure would be closed, but if we call save fig, the figure is not closed, so it will occupy memory unnecessarily. So we need to call plt close to save this signal. And the last thing that I like to do, because, well, this is quite, this function is not doing what it's supposed to. It should be just plotting, but now it's also saving. So what I like to do, I like to have a function like plot signal and save, right? And here I'll call plot signal again. And we can go again, signal and time. And signal and time, say none. But here what I like to pass is I like to pass this output path, which is a required argument, because if someone calls this, they want to probably, output the image somewhere. And now we don't use this constant anymore. We'll go plot signal and save. And here I will use this. Exactly. And here I'll just pass output path. And to create this folder automatically, so we can either call image output path make dir, but what I prefer to do is go output path parent make dir, and now this should work. So this is exactly what we wanted, and now plot signal only plots, it does need to save, and plot signal and save also saves. So let me maybe remove this folder and run this function again. Okay, and let us check this image. Perfect. We got exactly the sign that we wanted. And one additional remark is that this is a digital signal, right? But it's plotted as a continuous signal. So in the next video, I will show you how to plot a signal with individual samples so that we can see where each sample exactly lies. So this signal only, is so nicely continuous because the samples lie very close to each other. But if the samples are more apart, we may prefer to plot a signal using single points, and that's what I'll show you how to do in the next video that will be called how to stem your audio signal with Python. Thanks a lot for watching, and if you're curious how to learn more about processing audio using self-written software, I encourage you to check out my free audio plugin developer checklist that you can get at newwolfsound.com/checklist, and there I list every bit and piece of knowledge that I believe is necessary to become a full-fledged audio developer. And there I also have a section what is necessary to learn from digital signal processing and how you can leverage the power of Python for displaying, visualizing all the fancy DSP stuff, which stuff you can learn in the checklist. Thanks again for watching. Don't forget to subscribe to the channel, hit the thumbs up, and I see you in the next one. Take care.